This problem asks us to determine how many electrons need to be transferred upon complete oxidation of butyric acid to carbon dioxide and water. So pretty much we have butyric acid, which is a fatty acid, fully saturated fatty acid containing 4 carbon atoms. It reacts with oxygen. We'll determine how many molecules to form for each of the carbon atoms. Those carbon atoms need to be oxidized by molecular oxygen all the way to carbon dioxide. So we'll need to have 4 carbon dioxide molecules and water. So for balancing this reaction, we need to determine the molecular formula. So it will be C4H1, 2, 3, 4, 5, 6, 7, 8, or 2. And from here, it matches with 4 molecules of carbon dioxide. 8 hydrogens here in the butyric acid will be released as 4 molecules of water, and this gives us 4 oxygens for 4 molecules of water. Now 8 more oxygens from 4 molecules of carbon dioxide, and that will be 12. We will have 2 oxygens here, so we need to add 5 molecules of molecular oxygen. Now, what about the electrons transferred? For that, we would need to determine the oxidation state of all carbon atoms in butyric acid. And just to remind you about the rules how to determine the oxidation state. So we need to present each carbon. For example, I'm now looking at that carbon of the carboxyl group. Pretty much write Lewis structure for that. And this carbon forms 2 bonds with oxygen of the carbonyl group, 1 bond with hydroxyl group with another oxygen, right? And it forms a bond with carbon. Now we need to consider the electronegativity of the atoms forming a bond. And if those are the same atoms, such as we have for that carbon-carbon bond, now we need to assign electrons equally to each of the carbons participating in this bond. When we talk about bonds with more electronegative atoms, such as we have here for carbon-oxygen bonds, all electrons will be assigned to more electronegative atoms. So pretty much here, carbon just gets 1 electron, and we know that carbon atom has 4 valence electrons. It means that it is lacking 3 electrons. That's why the oxidation state for that carbon will be +3. Now, if we are considering, for example, this carbon right there, this carbon forms 2 bonds with carbons and 2 more bonds with 2 hydrogen atoms, right? Which are not explicitly shown in here, but we know that each carbon should form 4 bonds, correct? And if we do the same thing as we did in the first example, so we need to assign the carbon 2 electrons, 1 from each of the carbon-carbon bond, and from each of the bond with less electronegative hydrogen, carbon claims both electrons. So as a result, we see that this carbon claims 6 electrons, but it requires only 4 as the number of valence electrons. So we know that this carbon is more reduced, right? So the oxidation state here is -2. And we have 2 such carbons. So we determined +3 for this carbon, -2 for this carbon, -2 for the next carbon, because it also has 2 hydrogens. And the last carbon here has 3 hydrogens. So when we when we draw structure, Lewis structure, pretty much we draw the following thing. So this carbon will claim 1 electron from the carbon-carbon bond, and all electrons from carbon-hydrogen bonds. So as a result, the oxidation here we will have 7 electrons, and it will be 3 more electrons than the number of valence electrons. So the oxidation state of this carbon here is -3. And the oxidation state in carbon dioxide in each of the carbon dioxide molecules is +4, because 4 carbon doesn't claim any electrons because it forms two pretty much 4 bonds, right? Because we consider sigma and pi bonds separately, it forms 4 bonds with more electronegative atom. That's why it misses 4 electrons, right? So pretty much each of the carbon atoms would be oxidized way to the +4 oxidation state. So from +3 to +4, this is 1 electron donated by the carbon of the carboxyl group. Each of the -2 oxidation states, right, those 2 carbons, each of them, when they are oxidized to +4 oxidation state, will donate 6 electrons. And finally, the last carbon with the oxidation state of -3 will donate 7 electrons. And if we tally those numbers, it gives us 20 electrons that need to be transported, donated by butyric acid in order to form 4 molecules of carbon dioxide.